Good afternoon, everyone. This is our video number 2. I'm going to continue discussing the randomized complete block designs, and I've figured out some of the technical problems, so hopefully this will be a better video for you to be able to watch than the last one. So last day we were talking about the diet on male weight reduction example, and we had this table here. Now, I believe I had mentioned before that inside we have our means. What we have to realize is, though, because this is a randomized complete block design, there's only one observation per cell and 15 observations in total for this example. So 3.42 is the number of pounds of weight reduction for the male in group 1, which had the lowest, I believe, BMI score or BMI category that was assigned to diet 1, for example. And last day we talked about how to compute the ANOVA table and such for this. What we didn't get into was discussing specific contrasts of the different diets. So remember the ANOVA test, if we look back at that, right, we could test for a block effect. Here we found that there was a block effect, which isn't surprising because we did the blocking because we had this idea that BMI would affect the amount of weight lost. And then we also had this test on the treatment effect. And I was writing I was going to put significantly equal, which didn't sound right. And then I changed it to different, but of course, then I have to get rid of the not here. So we found that there was a treatment effect, which is what we are interested in, but we don't really know what the effect is. We don't know whether diet 1 is better than the other diets, if diet 2 was better than the rest of them, or how they compared. So that's what our diet contrasts are designed to help us figure out. So here we have a couple of questions that we're going to work through, and then looking at what are the contrasts involved with them, how do we build confidence intervals and conduct hypothesis tests. So the first contrast involves comparing diet 1 to diet 2. So remember, these were the 2 new diets, and we just want to know, is one of the new diets better than the other? So the contrast of interest corresponding to this question is looking at psi 1, so psi we use to describe the contrast at the population level, and it's just looking at the difference between the two, mu1 minus mu2. And of course, when we want to translate this into a contrast, we need to write it as or realize that we have a coefficient of 1 out front of the mu1 plus minus 1 mu2 plus 0 mu3. So just from looking at this, we can already read off that A1 would be 1, A2 is minus 1. There's no mu3 here, so A3 must be 0. To actually estimate the contrast, we have to look back at our summary statistics. So we would estimate the means by their sample means. So x bar 1 minus x bar 2. So here is x bar 1 and x bar 2. So 3.684 and 3.668. That gives us a difference of 0.016. And then, if you recall from our discussion of contrasts in even the one-way analysis of variance, we take our pooled estimate of standard deviation times the square root of the sum of those coefficients, the AI squared over NI. What's special about the randomized complete block design is that all of the groups have B observations, okay? So it's a balanced in that way. The sample sizes are balanced. So we can actually simplify this because the NI is simply equal to B, and once it's a constant B, we can take it outside of the summation. So we're essentially left with SP times the square root of 1 over b times the summation of the ai squared. So it's a little bit simpler. Although if you worked with this, it would have been the same. You just would have plugged in b each time for each term. So working with contrast 1, remember we had a positive 1 and a negative 1 for A1 and A2, and then 0 for A3. So if we look at these, and then we have 1 squared plus minus 1 squared is 1 squared plus 0, which we don't need to worry about. And then that just gives us a 2. So 1 plus 1, which is 2. And then we've already calculated our standard deviation, pooled standard deviation previously. Remember, that was the square root of our MSE in the ANOVA table. So we're left with a standard error of 0.01556, etc. One note to make here, which will become more important later on, is that the standard error that we have here is actually the same for all pairwise comparisons. So the SE same for all pairwise comparisons. And why is that? Because if you're only doing pairwise comparisons, you're always going to have one, a positive 1 somewhere, a negative 1 somewhere, and a 0 for the other coefficient, right? It's just, it doesn't matter once we have to do this summing of the squares of those coefficients, it will always equal 2. So we'll always have that square root 2 over 5 in our standard error calculation. Okay, so if we wanted to conduct a hypothesis test, in our original question, remember up here, we had differs, so that's telling us that we want a two-sided test. And so when we do our hypothesis test, the null hypothesis is that psi1 is equal to 0 versus the alternative. That means we want to have, sorry, let me move this up so you can see it. So then that means that we will want to have psi1 unequal to 0. So a two-sided test in our alternative. Just as we've done since the beginning of the semester, the t is equal to our estimate of the contrast divided by the standard error of the contrast. And when we take that ratio, we get 1.02852, etc. Now, we have to look at this and evaluate whether we have sufficient evidence to reject the null. And under the null hypothesis, our statistic follows a t-distribution with degrees of freedom inherited from our SP. So if we look back at the ANOVA table that we had for these data, let me just see if I can pull it up for you. So it's on page 131. Then we can see that there were 8 degrees of freedom, and the square root of this value was our standard deviation down here, and it's on 8 degrees of freedom. So our p-value then for two-sided test is 2 times the probability that t is greater than or equal to our value of 1.028. And then we'll want to look this up in our table, our t-table for 8 degrees of freedom. So let me see if I can do that here. And we're looking for the value 1.028. So there's our 8 degrees of freedom. 1.028 would fall somewhere in here. So it's between 2 times 0.15 and 0.2, because this is giving the area in only one of the tails. So this is telling us that our p-value is between 0.3 and 0.4. Okay. And then clearly there is insufficient evidence to reject the null. So let's say at 5% level, there is insufficient evidence to reject H naught, and we conclude that diets D1 and D2 are not, so here we could not reject the null, so under the null they are not significantly different. Okay, great. So that's how we would do our hypothesis test. What about our confidence interval? If we wanted to build a confidence interval for that difference, we play the same game we have since the beginning. We have our contrast, or the estimate of it, plus or minus a t-value times the standard error. The t-star, again, is on 8 degrees of freedom. And if we look that up in our table, I don't think I can get the whole table here, but what we need is the one where you have for 95% confidence interval, 0.025 in the upper tail, and that's giving us the value 2.306. So I'll scroll that in a bit. So 2.306. And so that's our t-star. Okay, so we have the t-star. We just need to plug in the standard error that we got from the previous page. And so now we can see that the margin of error is 0.03587. And then when we actually calculate the confidence interval, we see that it runs from minus 0.02 to 0.052 pounds. Okay, so what we can also say from this is that it's not very surprising. So remember, D1 and D2 were not statistically significant. So the CI covers 0, which is in line with the result of our hypothesis test. Okay, so what about another type of question? If diets D1 and D2 are not statistically significant, then we might be interested in knowing, well, even if they're not different from each other, are they different from the control? And in particular, are they better than the control? So here we have better. This is indicative of doing a one-sided test. And the contrast associated with that is looking at or contrasting the average of the diets on D1 and D2 with the average or the mean diet on weight loss on diet D3. So if you wanted to think about what the coefficients are, we simply have to rewrite this as 1/2 mu1 plus 1/2 mu2 minus 1 mu3. Once we do that, we can clearly see that our coefficients are 1/2, 1/2 minus 1. We can estimate the contrast by subbing in the sample means for x1, x2, and x3, and we find that the contrast is 0.246. the standard error. Now this one, we're not going to get that 2/5 because it's not a pairwise comparison. This is something, it's just a linear combination of all three, so we actually have to go through and calculate it, i.e. we can't rely on the what we had on the previous, for the previous comparison. And so here we can see that this is equal to 1/2 squared plus 1/2 squared plus 1, which is 1/4 plus 1/4 plus 1. Obviously, if you have a calculator, you can just do it there, but that gives us 1.5, which is 1.5. And then we're going to have 1.5 divided by 5, so there's where we're getting our 0.3. And so we take the square root, multiply by our pooled standard deviation, and we have a standard error of the contrast being 0.01347, etc. Okay, so we've got the estimate of the contrast, we've calculated standard error, now we're in business to do a hypothesis test. So for the hypothesis test, we have the null hypothesis being that the contrast is 0. And here we have to do a little bit of thinking for what does it mean to be better. So remember, psi2 is equal to mu1 plus mu2 over 2 minus mu3, where mu1 and mu2 were the new diets, mu3 was the control or the standard diet. So we have to reason if new diets D1 and D2 are better than D3, then weight loss on D1 and D2 would be greater than on D3. So that tells us or implies that psi 2 would be greater than 0. So now we know that our alternative hypothesis should be that psi 2 is greater than or equal to 0. And then to actually build the test statistics, same as before, take the ratio C2 over the standard error of C2, and then we have our test statistic value of 18.2598. This is now a one-sided test, so our p-value is simply looking at let me make sure you can see all that. Okay, so our p-value is just looking at the probability t is greater than or equal to little t. That's on 8 degrees of freedom. And what we see is that 18 is a very, very large value that doesn't actually appear on the table. So we know that our p-value is less than 0.0005 because that's the smallest upper tail probability that's available on the table. So that is giving us sufficient evidence at the 5% level, 1% level. Those are the standards, or 10, 5, and 1. So we have strong evidence that psi 2 is significantly greater than 0 because that's what the alternative hypothesis is. And so then we can conclude that the mean weight loss is significantly greater on D1 and D2 compared to D3 in the males. In males, because remember, this was male weight reduction. What we don't have a gauge on from this test is how much greater is the weight loss on diets D1 and D2. And so for that, we construct our confidence interval. To build a 95% confidence interval, we do the same game as we had before. We have to calculate our T star, and again, it's on 8 degrees of freedom, so it would be the same value as we used for contrast 1. And now we see that our margin of error is 0.031, which is a little bit smaller than what we had before, but now we're doing a different contrast, which is larger. So we end up with a confidence interval of 0.215 and 0.227. There are a couple of points to make here. So this is the 95% confidence interval on mean difference in weight reduction. When contrasting D1 and D2 with D3. So from a statistical perspective, there is certainly a difference. From a scientific perspective, remember, this is all done in pounds. So if you have a new diet and it's great claim to fame is that it will help you reduce 0.215, or at the greatest, that we've got is 0.277, so less than 0.3 pounds. From a scientific perspective, you might think, well, that's not a great enough weight reduction for that diet, for diets 1 and 2 to be that considered scientifically better, but statistically, there is a significant difference. It's just that it might not be great enough for us to put the effort in to change the diet, depending on what those diets were, what they involved. Another comment that I wanted to make, so let's do this, comments. Diets D1, D2 give significantly greater weight loss, but scientifically, the increase may not be large enough, i.e., may not be worth it. What else? Another comment. So we defined this psi as the average of diets D1, D2 minus D3. If we had done psi 2, let's call it prime, as equal to mu3 minus mu1 plus mu2 over 2. So suppose we flipped it the other way around, then this is also okay, but we need to change the alternative. Okay, so the main reason is that when diets D1 and D2 are better, then psi 2 prime would be less than 0. So my point is, I've had questions throughout, even when we first started talking about contrast, about what direction does the difference need to be taken. And the main point is that if you're just testing for a difference, it doesn't matter. You're test statistic might become negative, the magnitude's the same, and when you go to do your t-test to find your p-value, you'll get the same p-value. But when you're doing a one-sided test, you can also use either one, but what you need to be aware of is what is your alternative, and then that will need to change depending on which way you did the difference. So this should be, oh, right. Okay, so need to use HA psi 2 prime is less than or equal to 0. Okay, all right, so that is, oh, actually, no, should be less than 0. Okay, so that is it for specific contrasts. If you're in the situation where you didn't have a specific set of contrasts that you wanted to test, and what you wanted to do was just conduct all pairwise comparisons, then we can do that as well. In particular, we're just introducing a little bit more notation. So TIK is to denote the particular contrast we're doing. So if you note here, I'm going to make this a little bit bigger, then you can see that it's TIK is equal to X bar I minus X bar K. So IK is telling us the direction of the contrast that's going to be made and which two treatment means are going to be compared. And so this is taking the form of C over standard error of C, where standard error of C is always equal to SP over 2 over B. All right, so remember at the beginning of the lecture, remember at the beginning of the lecture, we talked about how it didn't matter which two treatment means are being compared. If you're looking at a difference between two means, we're always going to have the same standard error in a randomized complete block design, because the sum of your AI squareds is always going to be 2, and every group has treatment group has the same sample size, which is B observations. So that's our standard error there. And then the degrees of freedom for our test statistic is inherited from the pooled estimate of variance. So here we have degrees of freedom equal to 8. And now we have two choices of how we want to go about doing the comparisons. So the first choice is to ignore the fact that we're doing multiple comparisons. Difference. So this is ignore multiple comparisons. And so really what that means is when we look at our differences, we just have to compare our test statistic to that critical value T star. For the weight loss or the weight reduction diet study, if alpha is equal to 0.05, remember we said degrees of freedom equals 8, then we use the same value we've been using with our contrast, which is 2.306. The other approach is the Bonferroni method. There are actually many different ways of dealing with multiple comparisons, but this is an easy one, and so this is the one that's often taught first. Accounted for. So the basic idea is that we say if we want any single test to be statistically significant, we're going to have to require more evidence so that we can, if two of them come up as statistically significant at the same time, we can say that as a family, all of those tests that actually are statistically significant. Operationally, what that means is that instead of comparing to T star, we use a new critical value, T double star, and I'm just going to rewrite what we have here. So alpha star star. So what we do is we adjust our significance level to be the nominal level, so say that 0.05 divided by the number of tests. And then once we do that, we get awkward values of alpha star star. They may not appear in our t-tables, so we rely on software. So here our t star star is equal to 3.01576. Okay, so and again, that's for the diet data as well. So if we look at that data and actually do these comparisons, what do we find? We have 3 treatments, diets 1, 2, and 3. So there are 3 pairwise comparisons. I choose 2 is 3 choose 2, which equals 3 comparisons in total. Our standard error for each of those 3 comparisons is what we did for contrast 1, so 0.01556, etc. And so now it's easy to build what our test statistic would be. So, what are the hypotheses we want to test? Well, we need to compare mu1 to mu2, mu1 to mu3, and mu2 to mu3. These are, when we're doing these pairwise comparisons, we're always doing these 2-sided comparisons, which is why our declaring things different is easy. It's just comparing the magnitude of our test statistic against the T star or T star star. And when we look at T1, 2, we have X bar 1 minus X bar 2. So again, just to refresh our memory, when we look back at our data, we had 3.684 for X bar 1, 3.668 for X bar 2. And again, these are going by the treatment means, and then 3.43. So that's what we have up top is the 3.684 minus 668. We're going to divide by that standard error that we calculate on the previous page. We come up with a test statistic value of 1.0285. When we compare mu1 to mu3, again, we just have to plug in X bar 1 and X bar 3. We come out with a much higher value of our test statistic, which is 16.3277. And for mu2 equaling mu3, we come out with this test statistic value of 15.299. Okay, so just to, let me back this up a bit. So these are the comparisons that we're making. And we have, this is the first one, the second one, and the third one. And now at this point, we have to decide which type of test are we doing, the least significant difference or the Bonferroni method. Least significance difference is easy in that we don't actually account for any of the multiple comparison issues. We simply need to compare our test statistic with 2.306 for these data. And what we find is that the mean weight loss in males on diet 1 is not significantly different from the mean weight loss on diet 2. Why is that? Because we have T12 is equal to 1.029. This is less than 2.306, which is equal to our T star star. If we look at comparison 2, we find that the mean weight loss in the males on diet D1 is significantly different from the diet on D2. Why is that? That's because 16.33 is much greater than our T star star. And for a third comparison, we had 15.29 and 15.99 is also much greater than our T star star. So we conclude that there is a difference and that the mean weight loss in males on diet D2 is significantly different from that on diet D3. And remember, D3 was the control diet. So that was what we found here. You might also think, well, what if we did the Bonferroni method? Does it really make a difference? In this setting, particular scenario, we're only doing 3 different comparisons, so it may not make a difference. When you have a larger number of tests, it certainly starts to become much more of an issue. But let's see what we get here. It also depends on how big those differences are, right? So for the Bonferroni method, and this should have 2 R's, 1 N, we were doing 3 comparisons in total. So as we saw on the previous page, alpha star star would be 0.05 over 3, which gives us 0.0166. So saying for any individual test, we want the significance level to be much stronger, to be 0.0167. And that's so that as a family, all 3 tests, if they come up significant, then simultaneously they are. And as a family, we have this alpha level of 0.05. But at the individual level, it's 0.0167. Again, this is a hard value to look up in our tables, so we use software, which gives us the value T star star equal to 3.01576. And now the rule is, and actually let's do this on the previous page as well. I just want to sort of highlight what the rule is, this LSD method. This is kind of telling us what the difference is. And for the Bonferroni, this is our rule. So we also, again, compare a test statistic, but now it's to a much larger value, 3.01576. And then when we look at the actual data and the test statistics we had, then we actually come to the same conclusion. So T12 is equal to 1.03, which is less than 3.02, which is our T star star. And then we had our test statistic 2 was the same, 16.33 is much greater than T star star, and 15.299 was greater than our critical value T star star. So we actually draw the same conclusions that the mean weight loss in males on diet D1 is not statistically significant from diet 2, but D1 is significantly different from D3, and D2 is significantly different from D3. If we want to build our simultaneous confidence intervals for the difference between the means, then we build them looking at an estimate of the difference plus or minus our T star star, which is from the Bonferroni method, times that same standard error. So we've got the 2 over B. And now we're in business. It's easy to do this for our diet study data. So for the diet study data comparing mu1 to mu2. We're not going to, well, we actually already looked at mu1, we already looked at mu1 minus mu2, but we're basically doing it again here. The main difference is when we did it as in that contrast setting, we used a different T star because there we were interested in that specific contrast. When we're doing the pairwise comparisons and then these simultaneous ones, we need to change this T star to a T star star. So that's the big difference from what you saw at the beginning of this lecture. But we plug in the difference. So for mu1 and mu2, we have, so yeah, this should actually be mu1, x bar 1 minus x bar 2 times our standard error. We get our margin of error of 0.0469, and the actual estimated difference, or the confidence interval for the difference, is minus 0.031 to 0.063. So we can see the difference is small, and the CI covers 0. So this is giving us another picture of not only is it not significantly, significantly different because it covers 0, but also it's actually not that difference. Remember, we're talking about pounds, so it's minus 0.031 pounds up to 0.063 pounds is what the estimated difference is between the two new diets. For the other two contrasts, or I should say pairwise comparisons, we have mu1 minus mu3, mu2 minus mu3. The margin of error is going to be the same in both because our standard errors are the same. And so we get this difference of 0.207 to 0.301, or 0.191 to 0.285. So there are a couple of things we can also comment on here. We certainly see now how we can compute them, but what we can also see is that these have two confidence intervals have large overlap, which makes sense since D1 and D2 are not significantly different. And what we can also see is that the magnitudes are also not that great, right? And that was reflected in the contrast 2 confidence interval that we also conducted. So the fact that it's small is just sort of another sort of way to, when we look at our data, we want to make sense of it within the context of what it is that we're studying. So to go off and say that this is a great way to lose weight. Actually, there was an example in a real world example. There's a commercial for something called Lipocine, and in there they comment on how in clinical trials it's come out to be have a statistically significant difference in weight loss. But when you go in and you read the fine print, it was one of these types of scenarios where the weight loss was something like less than a pound or something. It was very small. Yet they charge money for these. For the use of the pills that need to be taken. So when we look at these different types of, there's sort of a broader picture, not randomized complete block designs, but when we're trying to test a statistical theory and we go back, we translate our question of interest into these statistical questions. But then once we actually conduct our tests and our confidence intervals, we should always go back and relate it to that question of interest and see, is it also scientifically meaningful result, not just a statistically significant result. So there's a big difference between this. So we can also, I guess, make a comment about that here. So always good to think about results in terms of both statistical significance and scientific meaningfulness. Because we may find statistical significance, it may not be scientifically meaningful. And when it's both significant and meaningful, that's great. Okay, so I'm going to end the lecture for today at this point. I still need to get you, I told you that I would try to record the lecture for the lecture that we missed to go over those notes. And your test 3 more or less will go up to this point of our notes. So if you look at formula sheet 3, it also ends at these multiple comparisons for randomized complete block designs. Soon I will, or for the next lecture, I'll be posting notes on two-way ANOVA from the textbook, chapter 13 in our textbook. What you'll see as the big difference between what we've discussed and what we have there, I think there are 2 issues. One certainly is that we will be looking at the interaction between our 2 factors. We won't have interest just in one and the other one's a nuisance, but rather the 2 of them are both important factors that we're interested in studying. And then sample sizes might also be another difference that we see between them. But certainly the main thing is that the interaction is what we don't have. Okay? All right, so I will close off there and talk to you guys soon. Bye.